Wind Power students, Dr. John Schrage here, and we're continuing now to understand about winds in the Earth's atmosphere in terms of how we can use the forces that are at work on an air parcel at any given time and explain what that air parcel is going to do in terms of its motion. Now, we've already talked before about, in the last lecture, about the geostrophic wind, which was an approximation to what real observed winds are doing when you are up in the free atmosphere, where you are high enough up in the surface, above the surface of the Earth, that you could make certain assumptions about what the flow was going to be doing, and end up with this relatively simple idea that, well, your flow is going to be more or less parallel to isobars, the contours of pressure, and it's going to keep low pressure to its left and high pressure to its right, and so on. But in order to do that, you had to be willing to stomach certain assumptions. There was this assumption that the winds were not going to be changing with respect to time. At least not like in the immediate, time frame. On the scale of at least the next few minutes or something like that, the wind could be assumed to be basically in some kind of steady state. 2, you needed to also be able to assume that friction was not playing a role if you were going to be able to make this geostrophic approximation. And 3, well, that's actually kind of a lot like assumption 1, but the forces that were at work, namely the pressure gradient force and the Coriolis force, had to balance. And by balance, we mean they had to add up to 0. See how that's related to the winds are not changing with respect to time by Newton's second law. If the forces didn't add to 0, there would be a net force, and then by F equals ma, Newton's second law, there would be an acceleration on the air. It would be changing its velocity with respect to time. Well, if I just pull up a diagram here that shows the vertical structure of the Earth's atmosphere, oh my goodness, and I got up to about 100 kilometers on that particular diagram there. Well, for the vast majority of the depth of the Earth's atmosphere, this is going to work just fine. We really don't need to worry about friction anywhere near, any of these layers of the Earth's atmosphere, unless we're going to start zooming in a little bit. Now I'm going to start stretching that diagram out so we can kind of see it a little bit closer to the surface of the Earth here. But even down, well, actually, if we just look at the troposphere, just the part of the Earth's atmosphere where everything you and I would call weather happens, actually most of that troposphere is actually plenty high up too. We really don't need to worry about friction up there, and geostrophic wind approximation will work just fine. But, we don't generate wind power up through most of the depth of the troposphere, the free atmosphere. Actually, even the tallest wind turbines and so on, and the floating ones, I can't think of the right word for that right at the moment, are tethered wind turbines, are all in the boundary layer. Remember the boundary layer? That's that lowest 1 to 4 kilometers of the Earth's atmosphere. Depending on the time of day and stuff like that, the thickness of the boundary layer will change quite a bit. That's where we're worried about wind power, and I think we're going to need to worry about friction. In fact, we're going to have to say that we can't live with that second assumption anymore about the flow is not affected by friction, and so I'm going to cross that out. Can't make that assumption anymore. It sure would be nice, though, if we could keep that first assumption. If we could make some kind of if we could assume the winds are in some kind of steady state, at least on the short term. Yes, obviously the winds are not in a steady state over like periods of hours or days. They're changing. But okay, at least for the next few minutes or something like that, the air parcel will just be continuing in a constant direction at a constant velocity. We can make that assumption. But let's see, if I want to make assumption 1 that the forces aren't, that things are not changing with respect to time, but I can't assume that friction is 0, I guess then I've got to stick friction there into assumption 3. Apparently we have to assume that all 3 vectors, pressure gradient force plus Coriolis force plus friction now, are going to add up to 0. They're going to be in balance. Oh, remember we talked about that in the last lecture, that human brains hate that. It's really hard to think about 3 vectors at the same time and try to figure out, gosh, if this one's a little longer and this one's turned a little this way, how are we going to add that up to make 0? That is really hard. Well, too bad. If in the boundary layer, we're going to have to start thinking about that. Okay. Alright, so we're going to be in the boundary layer. We're going to be trying to figure out what the winds are doing. We're going to have to come up with some kind of balance involving 3 forces that's going to be describing how the winds are different in the boundary layer than they are up in the free atmosphere. Okay, now up in the free atmosphere we had this groovy, if somewhat strange name, the geostrophic wind, for the approximation that we were making. It would be brilliant if we had a lovely name for that in terms of boundary layer winds as well. And your book makes a bold choice here. Your book decides to call these winds geostrophic winds also. Oh, Dr. Shruggy's having chest pains. That's terrible. That's absolutely dead wrong, okay? No, 1,000 times no. That is not the geostrophic wind. The geostrophic wind explicitly cannot have friction involved in it. And in the boundary layer, we are going to be having to take friction into consideration, okay? I did some research on this because I've never seen anybody do this except when students were making mistakes on tests. I've never seen anyone call these winds in the boundary layer geostrophic winds the way your textbook is. I thought, well, maybe this is like a language problem. Your book, as you probably have noticed, is written by an author from Denmark. Maybe it was a translation issue or something. That's a little hard to run down. I thought maybe that's like an engineering or a wind power term, but I couldn't find any place else where they made that term. In fact, in the process of trying to figure out why they called these winds in the boundary layer geostrophic winds, I found out that, in fact, if you look through other sources of information like other engineering topics that involve the winds and so on, in the boundary layer they use other words other than geostrophic wind, and they're wrong too. For example, I found you wouldn't need to know this, but I found a textbook that referred to these winds as quasi-geostrophic winds. Okay, there is such a thing in meteorology as a quasi-geostrophic wind, but quasi-geostrophic winds they're not winds in the boundary layer. That is a different topic altogether. I also found another source that called them semi-geostrophic winds. Well, I mean, I get the idea. Semi-geostrophic, it's kind of like geostrophic winds, but now maybe they're in the boundary layer. But again, semi-geostrophic is actually a defined term in meteorology textbooks. It means something particular. It does not mean winds in the boundary layer. All of this just makes me very, very sad. But the truth of the matter is, the actual term that meteorologists use for winds in the boundary layer is just plain horrible. The correct term, actually, for the wind approximation that we're going to be using in the boundary layer is the Goldberg Mon Balance, named after the two authors of the original paper that explained it, Goldberg and Mon. Even meteorologists hate that term. In fact, if you just go, I had to show you a screen capture of this just to show you how crazy this is. If you just go and do a Google search on Goldberg Mon Balance, you get a whopping 6,700 results. How many terms in English can you do a search on in Google and get merely 6,000 results? Okay, now part of the reason why it's so slow is everybody misspells the word Goldberg, but it doesn't change the fact that even meteorologists hate this term. But as you're going to see, we're actually going to get to dodge a bullet on this. For the time being, anyway, we're going to be able to not call these winds in the boundary layer geostrophic and avoid having to commit ourselves to a term. But we are going to have to keep in mind that your book is going to be using the word geostrophic wrong in some contexts. They're going to be calling some of these winds near the surface, or at least in the boundary layer, geostrophic when they are not. So we're going to have to be very careful, and I'll have to be very explicit when we are talking about these winds in the boundary layer. Make sure that we're using the words right and catching it when they're using the word geostrophic in an odd way in your textbook. Alright, before we move on to part 2 of the lecture and start picking apart, well, how will these winds in the boundary layer work, let's actually answer 2 quick questions. Question 1. Our concept of the geostrophic wind was a good approximation to winds in the A, boundary layer, B, free atmosphere, C, surface layer, or D, Ekman layer. Where was the geostrophic wind a good approximation to what observed winds were doing? Kind of a review question. Alright, make a choice from those 4 options and get a little feedback before you move on to question 2.